Good afternoon. My name is Juno So. The research topic I am going to present today is prediction of localized muscle fatigue using system dynamics simulation during construction manual handling tasks. In this presentation, first I give you a brief background and introduction of my research. Then I detail fatigue model using system dynamics that I developed. Next, I will present results from the model. Then I will conclude with a presentation of summary and future research. Introduction. Construction industry is labor intensive and over 40% of construction workers are performed by workers. Construction tasks involves manual handling with heavy objects and repetitive tasks. As a result, construction workers are frequently exposed to work-related fatigue, which may result in work-related musculoskeletal disorders and performance loss. A management consultant, Peter Drucker, famously once said, "If you can't measure it, you can't manage it." This implies that we need to measure fatigue to prevent undesirable fatigue during construction tasks. There have been tremendous research efforts to measure fatigue. There are several definitions on fatigue, but in this research I focused on localized muscle fatigue. Previous methods can be categorized into direct assessment, indirect tests, and model-based approaches. Even though these methods provide a valuable insight to measure muscle fatigue, they have several limitations such as the possibility of interference with ongoing work under real conditions and their applicability to only static conditions. To address these issues, I applied simulation-based approach to using system dynamics. Simulation is a useful tool to understand the components and interactions in a complex biological system. Especially, system dynamics, that is a dynamic and continuous modeling tool, helps to develop a biological system model. Since it was developed in the late 1950s, system dynamics has been used to analyze industrial, economic, social, and environmental systems of all kinds. With its analytic capability, system dynamics provides an analytic solution for complex and nonlinear systems. System dynamics modeling used stock and flow diagram and causal loop diagramming to represent a modelless understanding of the system. My research proposes to quantify localized muscle fatigue during construction tasks using system dynamics modeling and simulation, which reflect physiological responses related to the development of muscle fatigue. Fatigue model using system dynamics. I developed a fatigue model based on physiological responses related to fatigue. First, I defined muscle fatigue as a loss of maximum force generating capacity. Also, I assumed that the maximum level of force is considered as a tolerance limit for force exertion in this research. This assumption explains the relationship between fatigue and injuries. A combination of muscle fatigue and microstrain injuries can also result in diminished tissue tolerance as shown in the right figure. The reduced capacity of the tissue due to fatigue failure may cause cumulative trauma failure even in the low level of exertion. In addition, previous researches found that three major components play important role in muscle fatigue. Those are fatigue of the energy generating system, accumulation of metabolic byproducts, and blood flow. I modeled these three key components using system dynamics. This is the fatigue model using system dynamics. This model consists of four parts: muscle contraction, energy consumption, fatigue substances, and fatigue. I'll explain each part in the next slides. First, muscle contraction. Muscle contraction is a source of force or power output, and muscle contraction level is determined by required exertion and maximum voluntary contraction level, which means maximum force that one can exert. For example, if the required exertion is below MVC level, muscle can produce the amount of contraction for required exertion. However, the required exertion exceeds MVC level, one can exert forces as much as the MVC level. The next step is energy consumption. There are two ways to provide energy for muscle contraction: aerobic and anaerobic metabolic processes. The anaerobic processes have a higher power, which means that they use more energy than the aerobic processes. So I reflect the differences on energy consumption rate between aerobic and anaerobic processes in the model. Also, because depletion of energy is not important factor in terms of fatigue, I assume that energy reserve level on muscles can be recovered quickly. Fatigue substances. The primary cause of muscle fatigue is potassium and lactate ion concentration in muscle fibers, which result from anaerobic metabolic processes. Those are known as fatigue substances which interfere with muscle contraction. However, the fatigue substances are removed from the muscle by the blood over time. So I modeled these relationships quantitatively based on the findings from the previous research. The final step is the process of the development of fatigue. Even though causal relationship between fatigue substances and muscle contraction has been identified, quantitative relationship has not been fully understood. However, it is identified that the acidosis due to fatigue substances is more severe. There is a marked reduction of forces. From this finding, I assume that depending on the amount of fatigue substances, the degree of force reduction is determined. Research. This slide, this slide shows the dynamic changes on variables due to static sustained exertion. At first, muscle contraction is dramatically decreased when the MVC level meets the required exertion level. The energy reserve on muscle decreases due to muscle contraction, but it is recovered quickly after finishing muscle contraction. Fatigue substances also increase due to anaerobic metabolic processes, and it takes much time to be recovered. I also tested dynamic force exertion. For this test, I used 0.5 of required exertion level with 10-second interval. The results prove that the model is also suitable for dynamic conditions. I couldn't validate the model with actual data. Instead, in order to test the reliability of the proposed model, I compared the results from my model with those from previous researches. First, I focused on failure to produce the required force. Allen et al. Identified that increases and decreases in required force, maximum force, and fatigability will change the time to exhaustion. The results from the model showed similar patterns with the finding. Increase in required exertion results in reduction of time to exertion. In addition, higher required exertion causes earlier onset of exhaustion. I also compared the endurance time from the model with previous researches. Endurance time is maximal duration for a certain level of force exertion. In many studies, fatigability is examined by assessing the endurance time. I found that the model showed similar results with previous studies. I also tested the model by comparing recovery time. Previous researches found that after 2 minutes of sustained MVC, it took about 5 to 10 minutes to be recovered from fatigue. The results from the model coincided with the findings by showing recovery time ranging from 7 to 15 minutes. Conclusions. So far, I proposed fatigue model in system dynamics. This model reflects physiological responses related muscle fatigue and focused on quantification of muscle fatigue, which is defined as a reduction of force generating capacity. I also compared the results from the model with the findings from previous researches. As a future research, the model needs to be refined because there are too many assumptions. In addition, validation of the model is required. For validation, on-set EMG tests, which identify fatigue level directly, will be useful. References. Thank you for your attention.